Hey, Morgan.
Morgan.
Hi, Morgan.
And
Biscuits.
There we go.
Is there not over people?
Everyone else is here?
Oh.
This is my highest percentage attendance of this whole week, this class. Good job. That means 2/17 are gone. 11%, 12% maybe. Way more in other classes. Okay, here we go. Oxidizing and reducing agents. The strongest oxidizers have the most positive reduction potentials. That means the biggest losers will lose the easiest. Shocker. And the strongest reducers have the most negative reduction potentials. I never write that down. I never. I hate when that happens.
Oh my gosh.
Feel like Kyle just said something rude. Good. What you said won't really be heard though. This new mic's much better at just picking me up. That would be better, yes. It's my antidepressant. Okay. We good with that? Did you write what you needed to write? The greater the difference between the two cells, the greater the voltage of the cell. Okay, good. All right, now, what does this have to do with last chapter? Well, of course, we can figure this out. So, delta G for a redox reaction can be found using the equation delta G equals negative NFE, where N is the number of moles of electrons transferred, and F is a constant. The Faraday. 1 Faraday is 96485 coulombs per mole, or the same number, joule per volt mole. You just need to remember that. Well, actually, you don't have to remember that. That number is given to you. But coulombs per mole means we can use it in a picket fence, which we will do later. When you write out, if you were to ask to do one of these, the moles of electrons transferred, if it's Zn and it goes to Zn plus 2, then there was obviously a movement of 2 electrons, right? So that would be from here to there, if we wrote it this way. The 2 electrons, that would be the 2 moles of electrons would be involved. Okay? So it's just the coefficient we've been putting in front of E this entire time. So it really isn't that bad. Now, E, it doesn't say on here. What do you think E is? E is the thing we just calculated, essentially. Yeah. This thing. So under standard conditions, delta G standard is equal to negative NF E naught of the cell. We do not have to account for these under non-standard conditions anymore. It's kind of weird my email was showing there, but whatever. So we will not have to learn the Nernst equation and how it applies to these problems. All right, we should probably do a problem like this. So will you find me delta G naught when you have iron, I'll make it easy, plus oxygen goes to Fe2O3. All right, and we'll say it's under standard conditions. 96485 is the constant that you need. You will need to find this by using Appendix C. Okay, so speaking of school lunch, let's do this like one bite at a time. So we got to find N, right? F is right here, so that one's not hard. You all right with that so far? And we got to find E. So N, first off, we got to find the number of electrons transferred, essentially. So F is 0, and Fe over here becomes a what? Plus 3. O is a 0, and over here it becomes a minus 2. You okay with that? So O will be reduced, Fe will be oxidized. You okay with that? Now, there's a transfer of 2 electrons here and 3 electrons here, which won't work. So really, what do you think it's going to be when we balance this out? We find out. It's going to be 6 most likely. It could be a multiple though. So when we balance this, I see a 3 and a 2, so I got a 3 right here. You good with that? That puts a 2 right here, correct? And that puts a what right here? 4. All right. So we have, this is tricky, we have 3 oxygens gaining 2 electrons twice. So what's the total transfer here? It's 12. All right. And what's 4 times 3? 12. Okay, so now, guess what we have right here? We have negative 12. And then there's F. All right. So we have 2/3 of them. So now we just have to calculate E naught of the cell, right? So, I don't know. Do I remember right that it's cat minus an? I don't know what you mean.
Okay, so it's 12 for the O's, right? And it's 12.
Yeah, they have to be equal, yes. They always have to be equal. Right. Then you screwed up bad. Yeah. So just remember this. E cell equals cat minus an. What happens at the cathode? The red cat. And what happens here then? Ox, right? So now I have reduction. Which of these is reduced? The oxygen. Okay, so I have O2 going to O minus 2. Now, is this in your table? This is not in your table. Is that why you're all lost? It's really not in your table.
Oh, wait. O2. They all go to H2.
Okay, well, that would be my fault then. Why would that not be in your table? So let's just make a number up and go with it. Sound okay? All right. So well, let me find something that it would be close to. So it's going to be similar to fluorine, but not exactly the same. So fluorine has a positive 2.87. So let's call this a positive 2.5. And we don't know. We're just making that up. It has one. I can't imagine why it's not in the table. Okay, whatever. So that's positive 2.5. Then did iron have one? That's the Fe. Oh, Judas Priest. This is super annoying. Okay. Well, let's just use that 0.771. Oh, now I know why this was harder. All right. So which one's reduced again? Oxygen. 2.5 minus positive this time, right? 0.771. And what do you get? This is positive or negative? Positive. What does that mean? Okay, it will actually happen. Does iron rust? Yeah, it does. So that is something that should happen. All right, now we're really going to use this number up in this equation, right? It is now this value. So here we go. Delta G. Oh, Nelly. Okay, thank you for nothing. We'll just do it right here. Delta G equals negative 12. That's the electrons transferred. Faraday is 96485. And then we have this, was it 2 point what? Or 1.7? 29. You plug that in. Okay, what do we end up with? Negative what? 2 million. That's a big number. All right, and that's joules, because this was, F is joules, eventually, whatever. Okay, so, or 2,000 kilojoules, right? And it's a negative value. What does that mean? Well, delta G, negative, means it is spontaneous. Is spontaneous. Which, once again, does iron rust? Yeah, we know it does. It takes time, but it definitely rusts. We're just finding essentially whether it happens and what type of work could be done with it, which is slightly different from the amount of voltage. Now, I realized a few things in this problem. This would not actually work, and I know, whatever. This is not necessarily a reaction that would work well in an anode and cathode situation. So that's probably why we don't have that in there. you need more of something happening in a solution, and this is just oxidation of iron. So that's probably why those two values aren't there. But anyway, the math in the process is fine, but that's probably why they're not. Okay. I don't know. I'll find one in the book, and that will probably be better. Let's attack the last couple of things in this. And that's applications of oxidation reduction reactions. You should read this on your own, because I will scratch the surface barely. Batteries. Look how much text is on this slide. None. All right. This thing is called a lead acid battery. Anyone know where we find these? All right. That's your car battery. It takes advantage of a very complicated reaction between your acid electrolyte, your lead grid, and like it seems like it would just be those two things, but there's way more in a lead acid battery than just those things. And then you have your battery here. Does anyone remember back in the day when they used to call a Duracell battery the copper top? Ever heard that term? All right. Well, a Duracell battery literally has that kind of copperish looking top, right? But it also literally is copper on the top. And then usually zinc on the bottom. Now, it's not just a chunk of copper, or the battery would cost a ton of money. But it's taking advantage of that copper and zinc reaction that we drew a while ago. So batteries, they create electricity through the transfer of electrons, and we put them in a circuit so we can get work out of them. All right, there's the same idea. Alkaline battery, your little gasket, that's the thing when your battery dries out, that will kill it also. The other way a battery dies is the electrons go from one side all the way to the other. If it's a rechargeable battery, you just plug it in and you use the electricity from the wall to force the electrons to go the way they don't want to, so that when it's unplugged, they will go the way they want to. Yeah, Blaine? Oh, okay.
How do you keep, because we learned that the games mass. How do you keep it like solidified?
All right, well, it can. All right, and it doesn't necessarily, in these type of batteries, it's not like plating, which is coming up in the next two slides, in that drawing I did before. So there's nothing in this solution, because there really isn't a solution. It's just a damp gasket in between them. There's no real transfer of mass in an alkaline battery like there was in the other ones.
So are all rechargeable batteries?
No, most of them are lithium ion, but there's definitely other types as well. All right, then a hydrogen fuel cell. 10 years ago, these were going to change the world, and maybe they eventually still will. But you take hydrogen, you take oxygen, and you keep them separate, and then you let them react. And as that reaction happens, an electron has to be transferred from H to O, and we can use that for work. Each individual one gives you 1.23 volts. Any ideas where that came from? That came from E of the cell for H and O. This is the voltage you can get. Now, you can't drive a car on 1.23 volts, but if you put these all in a series, they just keep adding. And these hydrogen fuel cells in vehicles and buses have thousands and thousands of individual fuel cells that give off 1.23 volts each. The nice thing about this is the exhaust is just water. It's pretty cool. The problem with the hydrogen fuel cell right now is finding just pure H2. Like there's plenty of hydrogen. It's one of the most abundant elements on our planet, and it's the most abundant element in the universe. But just plain hydrogen needs to be separated out from water. And in order to separate hydrogen out of water, it requires 1.23 volts. Okay? It takes the same amount of energy to make water go to H2 plus O2 as it does to go the other direction. All right? And so the problem, it's really twofold, is that this is a net energy not loss or gain. It's a clean car, but it took energy somehow to separate that water in the first place. And then also right now, they are still working on this. To get the size of a hydrogen fuel tank into a vehicle that will hold enough hydrogen is not practical right now. So you'll see hydrogen fuel cells like in a bus. They're pretty common in our country now, but that's because they can have huge tanks of hydrogen. There's one country on the entire planet Earth that leads everyone in hydrogen fuel cell vehicles and in hydrogen fuel cell electricity, and that's Iceland. You know why? Okay, they don't have a huge infrastructure. They're in the middle of nowhere. Importing oil there is extremely impractical. They have a lot of water surrounding them. And one other thing there you go, thank you. They get all their energy for free. Iceland is on a volcano, so right underneath them is a free source of heat. They use that heat to produce steam, which they then use to create electricity, which they then use to break water apart and supply all their vehicles and energy needs that way. So it's pretty awesome. What'd you say? That's funny. Do you know the number one threat to Iceland right now is Bitcoin? Does anyone know how Bitcoin works? Okay. It's super, yeah, Bitcoin mining. This is, let me pause this. Sorry, kid. Hi, kids. All right, another application of this is corrosion and anti-corrosion. Oh, what?
Or something that splits hydrogen.
Well, it's not hard. You wouldn't do this. Yeah, but you can take a power cord to anything. Do not do this. But just cut it off, split the two parts, plug it in the wall, and drop it in your tub. You're going to get bubbles from one side and bubbles from the other, and one's hydrogen and one's oxygen. Do not. I said that 10 times. Do not do that. Do not do that. It can kill you. You touch the water, you die. You don't. You guys you're not listening to what I said. Okay. Anyway, corrosion is when oxygen from the air or a water droplet will react with iron, and the iron will be oxidized to become Fe plus 3 typically, sometimes Fe plus 2, sometimes Fe, but typically Fe plus 3 is iron oxide. All right, so you have that, and it makes this Fe2O3. That's the rust. It breaks the malleability of the metal down, the tensile strength, and everything. It goes down. All right, now this says and ... for the next slide, which is corrosion prevention, which is genius. If you've ever heard of galvanized steel, this is it. Most things that you just look at or interact with that are metallic are galvanized. And so instead of letting this happen in the environment with oxygen, they have the reaction happen before they send it out. And what they do is they put zinc they put zinc on the iron and it reacts and sticks to the outside of the pipe. And then the zinc reacts with the oxygen to make zinc oxide in a really, really, really thin layer. And sure, the zinc oxide itself is not very strong, but it's just a layer that is protecting the iron. All right, I put a fence in my yard a long time ago, and it had some painted posts, and it said warning, if you scratch or whatever, make sure you paint over your scratches, because the paint was the thing that was protecting the outside layer. If you scratch that off and scratch these zinc things off, then the thing will rust. But anyway, you can have, like this fence that surrounds the track, they'll probably rip it down long before it ever starts to decay or to rust. And that's because the manufacturer had it happen the way they wanted it to, not the way Mother Nature did. This is not like looking at one of these. This isn't a beautiful process. They'll look splotchy, all right? Because the zinc, the way it's added, the way it oxidizes, it will all be a little bit different. But that's how you can tell a galvanized pipe. And galvanized comes from a galvanic cell, and that's the same thing we've really been studying. Okay, now this, they always have one or two of these on the AP test, so be ready for this and the tests I'm going to give you. So quantitative aspects of electrolysis. Hold on, this might be out of order. There is no slide on electrolysis. Okay. So let me talk. I must have deleted it because there was a slide on what's called electroplating. Electrolysis. These are similar things. In electroplating, we use electricity to plate something, like we make a knife out of zinc. I know this doesn't look like a knife, but we want it to be called silver, so we plate it with silver on the outside. And that's nice because silver looks good and silver does not oxidize very fast, so it stays really shiny. Yep. Well, okay, I gotta be careful. It's how they do gold plating. Gold leaf is actually super, super thin gold sheets that they just rub on to stuff. So, but gold plating, how most things you see are gold plated. They might say gold leaf, but they're not. All right, so what you have in here is zinc metal and Ag plus. And what you do is you cause this to become negative, and the Ag will stick to it. It will stick to it forever. So unless it's scraped off physically. But anyway, the math we're going to do is we're going to determine the gain in mass of this thing. We can also determine the amps that we need to supply to this thing to get it to do what it needs to do. Everything on your car that is chrome is also plated. It is some base metal, and then they put chromium on the outside of it because it is extremely shiny and resilient. Now, electrolysis, that just means to cut apart with electricity. And that's what I did the first day of school. I used electricity to break this to H2 plus O2. But the math we're going to do is on electroplating. All right, so for any half reaction, the amount of substance oxidized or reduced is directly proportional to the number of electrons passed into the cell. Or the current. Sorry, that's your foot, huh? I thought I was kicking the chair. That's always awkward. Charge is measured in coulombs. A coulomb is an amp per second. That's going to be your relationship that can help things all tie together. So electricity can be thought of as a reagent in a redox reaction. All right. So, man, I haven't looked at this for a year, but I think we'll be all right. We have an amp is equal to a coulomb second. A Faraday is equal, 1 Faraday is equal, or it's equal to 1 Faraday over 96485 coulombs. I'm a little confused on my own self. Oh, I see what they are. Go ahead. So when we talk about these like coulombs, when we have aluminum going over to Al plus 3, that's where we would have our 3. I should say coulombs, our Faradays. So the coefficient of your electron movement will be the number you would put up here. Now, I don't think this is making very much sense because I should have reviewed it myself. But we'll work through a picket fence here. So it's already done, but we can walk through it together. So a question would say, calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten AlCl3 if the electrical current is 10 amps. All right, so you have two things that are given to you. You have the amps and the time. So there, we just said our amp is a coulomb second on the previous slide right here. Whoops. So amp, we're going the other way, is a coulomb per second, I should have said. So anyway, they relate to each other. So what we're going to do is multiply my time times my amps. Yeah, hour. Now, the time needs to be in seconds. And then we have these two ratios. Coulomb per amp seconds and Faraday for coulombs. So these are the way we can get rid of our seconds. And these are the ways we can get rid of our coulombs. That leaves us with a Faraday. So far, we've multiplied and then we've gotten rid of these units by using the picket fence. And we're left now with a Faraday. Well, the Faraday is related to the moles, and it's 3 moving from the Al plus 3 to the Al. So 3 Faradays, or 3 electrons transferred, for every 1 mole of aluminum. And once we get to moles, every one of us should know what to do from there. We then can get rid of moles on the bottom and put the molar mass on top. And we can find out that we, under those conditions, can get 3.358 grams of aluminum. You use the ratio of 96485 coulombs per 1 Faraday. And by the way, this thing is given to you on the AP test. Now, I like to simplify things, and you should also. So, in a problem like this, you typically take your 2 givens and multiply them and divide by the number of electrons and then multiply by the molar mass. Because there's a lot of steps, but that's ultimately what you did. You multiplied both givens and divided by the number of electrons transferred, and then just multiply by the molar mass. Yep, multiply your 2 givens and divide by the electrons transferred, and then multiply by the molar mass. Oh yeah, I had that crossed out. You definitely have to divide by that times that. Okay, now, on Monday, we're going to do another problem like this. We'll make sure you're good at these. And we're going to solve for amps instead of grams. So it's tricky. Thank you. I didn't even notice I'd crossed that out.